right, so number 17. Number 17 is the first question that was anybody asked. It says a disk of mass. So we got a mass. All right, everybody's gonna have a different mass. Held by an unstretched spring, and that spring has a length, and we'll call that L, and a stiffness, so it has a K value, and it rests on a frictionless table, so it's unstretched, uncompressed, so that's the length of the spring by itself. Orbited in a circle with an angular velocity. Okay, so we have angular velocity. By how much is the spring stretched? By how much is the spring stretched? Okay, so first of all, converting angular velocity, because angular velocity itself is not one of the things we generally have in this unit, but I did talk about it a little bit. Angular velocity is equal to 2 pi times the frequency, also equal to 2 pi over the period. So really, period would be equal to 2 pi over angular velocity. And the reason I mention that is because we don't have an equation with angular velocity, but we do have an equation with period. And that equation with period that deals with springs is period equals 2 pi square root of K over M. Okay. So let's see. Well, we have the K value. That's good. So going through this, we got the K value. We have the mass. That's good. The angular velocity. We have that. We have the period as well. So let's see. So what's the stretch of the spring? Okay. Well, okay. So that seems to be all solved for. So let's see. We need to find the stretch of the spring. So we need to know the force that's being applied. That equals kx. All right. So that's where the spring is stretched. That's the equation I need in order to find the spring that's stretched. All right, so I need to figure out that force. Well, since it's going in a circle, right? It's going in a circle and it has a radius. That circle has a radius, and then that circle also has a period as it goes around. So that's where period shows up again. Okay, so the spring force equal to kx. As it goes in a circle, that spring force is applying a centripetal force. So if you look at the net force equals mass times acceleration, the spring force is supplying the centripetal force. That equals mass times centripetal acceleration, which is speed squared over radius. Okay. Let's see. Spring force, kx, that equals mass times the speed squared over the radius. Okay. Next thing to know. I'm going to need another paper for this. So I got the K value. Again, I got the K value. I got the mass. I got 3 unknowns here. I got X, I got R, and I got the speed. All right. So this requires a little bit of extra manipulation. So Kx equals mv squared over r. And the extra manipulation is that the speed is equal to 2 pi times the radius over the period. 2 pi times the radius over the period. Okay, so if we take that and plug that into our equation, we'll get to that in a second. One thing I want to mention is the radius. If you think about the radius as it's going around, all right, as this is going around in a circle, that radius includes 2 things. All right, so the radius, as it's going around in a circle, is going to include the original length of the string, of the spring, the original length of the spring, and then it's going to include how much it's stretched. So that radius includes the original length of the spring, and then as it spins around, it's going to stretch as well. Okay, so I'm going to plug in radius into this equation as well. And what you get is you get kx, that equals mass times the speed, 2 pi r over the period, quantity squared, and we'll plug in the r in just a second, all divided by radius. Okay, so squaring everything in here, I get kx equals m times 2 times pi. I'm sorry, I messed up already. That 2 is actually 4 because I squared the 2. So square the 2 becomes a 4. Square the pi, it's pi squared. R squared. And then we got period squared in the denominator. And then we got another radius in the denominator. So one of those radii will cancel. Okay. So now let's plug in that radius. So kx equals 4 pi squared m times r, which is L plus x. Then we divide by the period squared. Now we have the k value. We have 4 pi squared. We got the mass, the period we can find, length of the spring, and so we need x and x. We need those two unknowns isolated. All right. Let me rewrite this. All right. Now to isolate my x, I've got to basically, I'm going to take all this to the other side because all this is a constant. So I got period squared, that comes in the numerator, times k. Then we divide by 4 pi squared times the mass. So all that is a constant. All right, again, the pi squared comes over, I'm sorry, the period squared goes in the numerator, divide by 4 pi squared and mass. And then we have the k is in the numerator and then the x is outside. And what's left over is L plus x. Okay. Now at this point, I would go ahead and get a number there. I'm not going to go much further than this because basically it would get really complicated with a lot of stuff going everywhere. I would just get a number for that. And once you get a number for that, you have an x over here and an x over here. So subtract your x. And then you subtract the coefficients, isolate your variable. Okay. So some value for that, then you isolate your x. The rest is algebra. All right. So this one's obviously a little bit harder than what I would expect you to do for the test. It's a little bit above and beyond, but it uses a lot of things together, which is kind of why I included in your all's homework. It's also why I made it the last question on the homework, because it's one of those that I intentionally put a little bit harder questions on there so that I kind of push you all a little bit, but I also give you all some of those points back. I don't know if you know this, but every homework I've been giving, it hasn't been out of, for example, this is out of 17 questions. I usually take it out of 16 or maybe 15 and a half questions. I give you all some of those points back because I do have harder questions on here. Okay. Other questions? Number 6. Okay. Number 6, it says, as viewed by a bystander, a rider in a barrel of fun in a carnival finds herself stuck with her back to the wall. Which diagram shows the forces acting on her? Okay, so it shows the a profile, person against the wall, and this is part of a barrel, effectively, that goes around, that spins around an axis. All right, you can kind of see that in the diagram above. So the question is, what are the forces that are acting on her? All right, so first off, we know there's gravity acting. Gravity's pulling down. We know that. But she's not falling. She's not accelerating in the vertical direction. So with gravity, there needs to be something upward. Now, if you think about this, what's the only force really that can push upward? Well, if you start thinking through your forces, normal force. It's not normal force because normal force is actually, she's not standing on a surface. It's not normal force would, in order to be upward, she would have to have a flat horizontal surface that she's standing on, and she's not. Now she's pushed against the wall, and just like any surface contacts, when you rub two surfaces together, there's actually a force of friction that's acting there. So the force of friction is actually what's holding her against the wall, or holding her up, balancing down gravity. All right. If you've ever been on one of these, as they speed up, you get stuck against the wall. But as it slows down, you can feel yourself kind of creep down the wall a little bit as the force of friction decreases. Okay. Lastly, as she is going around in a circle, there is a centripetal acceleration, which means there needs to be a net force towards the center of the circle. So there has to be some force keeping her in a circle. And if you think about it, the wall itself supplies that force, and this is actually our normal force. Okay? And there's no outward force. There's no outward force acting on her. Now, if you've been in one of these, it feels like you're getting pushed outward, but you're really not. You're actually trying to move in a straight line, and the wall is pushing you inward. All right, it's kind of like if you're standing on the ground, if you feel yourself being pulled downward, that's true, but you got that force, the ground that's pushing upward. And what you don't feel gravity in the vertical direction, you actually feel the normal force pushing up. Same thing here. The force of the normal force is pushing in. So that's what your free body diagram is going to look like. All right, next question. Okay. Number 4, it says if the rotation of a planet with a radius of, well, given radius, and acceleration. Okay, so this gets back to the gravitational force equation, which is what we did before before winter break. Okay, so the rotation of a planet. So a planet is rotating with a radius of r. So radius of r. Okay. And then the acceleration, so we've got a g value that's not the same as the Earth. Let's see, free fall acceleration increased to the point that acceleration is equal to the gravitational acceleration at the equator. What would the tangential speed be? Okay. So the rotation of a planet, we've got a radius. We have the acceleration due to gravity. The question is, what's the speed? What's the speed? So centripetal acceleration says the centripetal acceleration would be equal to the acceleration due to gravity, gravitational acceleration. All right. So it says free fall acceleration to the point centripetal acceleration is equal to that. So it states that in the problem itself. Okay, so centripetal acceleration is speed squared over the radius. The g value is given, the speed is what you're looking for, and then you're given the radius in the problem. So that should get you to where you need to go. So take this one step further, you get the acceleration that's given in the problem times the radius equals the speed squared. You should be able to get it from there. I'm going to take attendance real quick. There we go. Okay. Other questions? 14. Okay. Number 14. All right. Small moon of a planet has an orbital period. So we have the period as it orbits. And by the way, that period is given in days. You have to convert to seconds. And a radius. So that is in days. And you got to go to seconds. The radius is given in kilometers. You have to convert to meters. All right, so make sure you get base units on each one of those. All right, so you got the orbital period, you got the radius. What's the mass of the planet? Okay, so this gets back to basically what we did in number 4, where the centripetal acceleration is equal. The centripetal acceleration is equal to the acceleration due to gravity. All right. So if we take this back one step, net force equals mass times acceleration. All right. So where this equation comes from, the force of gravity is equal to that mass times centripetal acceleration. Now for the surface of the Earth, that's simply mass times acceleration equals mass times centripetal acceleration, centripetal acceleration. So that's where you get this equation up here. But if you don't know what the acceleration due to gravity is, or you don't know what that equation is, then we got to go to the big definition of gravity. So if you remember the big definition of gravity, that's gravitational constant times the mass of the planet times the mass of the moon. So those are the two objects applying a gravitational force between each other. All right. Sorry, I didn't have that in the frame. And then divide by the distance between the two squared. And then that's going to be equal to the mass of the moon, because that's what's moving in a circle, times its centripetal acceleration, which is the speed squared over the radius. Okay. So in this problem, we're looking for the mass of the planet. So that's that. All right, that's our question mark. Mass of the moon actually cancels, so we don't need to know the mass of the moon. That's good. One of the radii will cancel, one in the numerator, one in the denominator. And let's see, so what are we left with? We're left with the gravitational constant times the mass of the planet divided by the radius that the moon is orbiting, and that equals the speed squared. All right. So we isolate this for the mass. Let's see. Thing is, we're not given the speed. We are given the radius. But we can use the speed equal to 2 pi times the radius over the period. All right. Remember, the speed of an object is distance divided by time. So the distance of a circle, 2 pi r, radius is given, divided by the period given. And we can use both of those to find the speed. And we can use that speed over here, along with the radius and the gravitational constant. Now, if you don't remember the gravitational constant, it's on your equation sheet, 6.67 times 10 to the negative 11. Okay, other questions? Are we good with that one? Gravitational constant given, the radius is given. Make sure you convert to meters. The speed, 2 pi times the radius over the period, and then your only unknown should be the mass of the planet. All right. Next question. All right, number 12. Actually, I saw 8 first, sorry. Let's go to 8 and then we'll come back to number 12. Okay, so 8 is the second part of number 7. Number 7 says a car with a mass traveling on a flat circle with a radius, the coefficient of static friction between the yada, yada, yada. What's the maximum speed the car can go without flying off the track? Okay, so it says now the same car travels on a straight track and goes over a hill with a radius. What's the maximum speed without leaving the road. Okay, so as it goes over a hill, that hill effectively makes a big circle, at least it's a part of a circle, with a radius. The radius of the hill is given. Now, when you go over the hill, you got two forces acting on you. You got normal force, and you've got force of gravity. Now, when you go really fast, if you've ever, hopefully you've never done this and you never will, but if you go fast enough, you'll come off of that hill and you'll actually become a projectile as opposed to going in circular motion. The slower you go, you stay on the road, but as you go faster and faster, you eventually come off. So there's a point at a maximum speed where the normal force is very small and almost zero. Now, at that point, the force of gravity is essentially the only force acting on you. If you remember, when the force of gravity is the only force acting on you, then your acceleration is 9.8. And if your acceleration is 9.8 and you're moving in a circle, that means your centripetal acceleration is 9.8. Okay, so as you go over this hill, then your centripetal acceleration is going to be equal to 9.8. That's going to be equal to speed squared over the radius. Radius is given, maximum speed. Again, we take radius to the other side, so g times radius is going to be equal to the speed squared, and you can figure that out from there. All right, so the next problem, number 12. Number 12 is second part to number 11. So the car rounds a curve with a radius and a speed. What force must the road exert on the tires to hold it on course? So effectively, we're talking about the force of friction. Now we want to make a curve that's banked. So imagine that car going around in a circle. Imagine that's a horizontal circle. And as this car is going around in a horizontal circle, there is a net force towards the center of the circle. That's our centripetal force. But the question asks, if we bank the curve, banking the curve, what will the bank of that curve need to be so that it is the most comfortable ride? All right, so let's talk about the free body diagram first. All right, let's talk about the forces that are acting on this car. All right, so looking at the perspective of this point right here, there is a normal force that's going to be perpendicular to the surface. So normal force. We have a force of gravity that's downward. All right. If you go too slow, then you're going to have a force of friction that needs to hold you up the ramp, prevent you from sliding down. If you go too fast, that force of friction is actually holding you onto the ramp where you don't slide off the other way. All right, so too slow, you would slide down without friction. Too fast, you would slide up and off without friction. So when it says the most comfortable ride, it's essentially asking for, well, at what angle do I not need friction at all? At what angle do I not need friction at all? So what is the angle of this ramp so that friction is not needed? Okay, so normal force, it's going to have two components. It's going to have a horizontal component and a vertical component. Now the horizontal component, we'll say that's the parallel to the ground. Okay, the parallel component of normal force. That's supplying the centripetal force, right? If you remember, that direction is the net force. I'm going to do this in a different color because you don't put net force on a free body diagram. All right, net force is that way. The only force that's in that direction is the normal force. So the parallel component of normal force is going to be equal to mass times centripetal acceleration. The perpendicular component of normal force, right? So this upward part, that's balancing gravity. So the parallel component is providing the centripetal force. The perpendicular component is balancing gravity. All right. So how do we figure out that angle? Well, this, let's see, what angle? If we have, as the angle gets steeper, this angle gets bigger. So that angle and that angle are going to be the same. So that means if I do tangent of that angle, that equals the parallel component over the perpendicular component. Parallel component over the perpendicular. Parallel component, mass times centripetal acceleration. Perpendicular component is force of gravity. That's mass times gravity. All right. So the mass actually cancels. And if you know the centripetal acceleration, which is given in the previous problem, the information for that is given. You have the speed. So let's go through this. Speed squared over radius, and then you got g in the denominator. The speed is given in number 11. The radius is given in number 11, and then the acceleration due to gravity. And that'll be equal to tangent of theta. That'll be equal to tangent of theta. So the angle, that'll be equal to inverse tangent of that speed squared over radius times g. All right. How we doing? Other questions? All right, number 15. Use purple now. Okay, number 15. Satellite moves in a circular orbit around the Earth with a speed. So that speed is given. Now it looks like that speed's given in kilometers per second. That's got to be converted to meters per second. So keep that in mind. Determine the satellite's altitude from the surface of the Earth. Assume that the Earth is a homogeneous sphere with the radius, yada, yada, yada. Okay, so as this object goes around, so here's the object, here's the satellite going around, right? So that satellite's going to have a radius, how far out it is. Now keep in mind that it says altitude, and if you know anything about altitude, altitude is how far an object is from the surface of the Earth. Which means as you figure out the circular motion of this object, the circular motion tells you how far it is from the center of the Earth. So if you figure that out, if you know how far it is from the center of the Earth, if you subtract off the radius of the Earth, right, and that'll give you the altitude. So the radius of the Earth plus the altitude, that'll give you the radius of the centripetal motion. Okay, so let's get to that radius of centripetal motion first. So we got a force of gravity that is holding on to this object. The force of gravity is what's providing the centripetal force. So net force equals mass times acceleration, speed squared over radius. Let's see. So the speed is given in the problem. The mass of the Earth and the radius of the Earth is given. So that means, let's see. The radius of the Earth doesn't help me right now because the radius, the distance that the satellite is away, is not equal to that radius. So we get the gravitational constant times the mass of the satellite. So that should be an S. Mass of the satellite, mass of the Earth, divided by the distance between the two objects squared. That's going to be equal to the mass of the satellite times the speed of the satellite, which is given to us, squared, divided by how far away is that satellite is. Okay. So from this, we see the mass of the satellite is actually going to cancel. One of the radii are going to cancel. And what I'm left with is I'm left with the gravitational constant times the mass of the Earth divided by the radius. That's not the radius of the Earth. That's the radius that the satellite is going in a circle. And then that's going to be equal to the speed squared. Okay. So from here, I have the gravitational constants given in the question. It's also on your equation sheet, 6.67 times 10 to the negative 11th. And then I have the mass of the Earth, that's 5.98 times 10 to the 24th, given in the problem. Rearranging this, we bring the radius to the other side, so we get g times the mass of the Earth. And then bringing that radius over, we multiply by radius by velocity squared, but I need to bring velocity squared to the denominator there. Okay. So once you do that part, figure out the radius that the satellite is going around the Earth. Then you can use that up here to find the altitude. The altitude is going to be equal to the radius of the satellite going around minus the radius of the Earth. All right. Other questions? Number 8 was going over the hill. Okay. There we go. All right, so number 8. Number 8 is we're going over the hill, and it says, at what point, what's the fastest you can go and still remain in a circle? If you go any faster, you come off the hill, you become a projectile. So at a faster speed, instead of staying in a circle, you would make a parabola. Anyway, so effectively you get to a point where the normal force is decreased so small that it's effectively zero. Technically, it's not going to be zero because you're still going to be in contact with the ground, but it's going to be really, really, really tiny compared to the force of gravity. So if that's the case, then force of gravity is the only force acting on you, and that means your centripetal acceleration is going to be equal to the acceleration due to gravity. And then the centripetal acceleration, speed squared divided by radius, and then isolate your speed. All right, other questions? Rest of them pretty straightforward. Okay, number 10. Another paper. All right, number 10. So the coin is placed distance from its center of a turntable, initially at rest. We've got a turntable placed at a certain radius out. Okay. Turntable begins to rotate. It says when the speed of the coin is that amount, so it's got some speed. Now that speed is given in centimeters per second. That has to be converted to meters per second. So make sure you do that. The coin begins to slip. So what's the coefficient of static friction? Coefficient of static friction. Okay, so looking at a side view. So this is a top view of the coin as it's going around. Looking at a side view of the coin as it's on the turntable and it goes around in a circle. There's a force normal. There's a force of gravity, and then there is friction that's holding it on the table. Okay. Now the direction of the centripetal acceleration is toward the center of the circle, which is horizontal. So the question is, what's the coefficient of friction? Coefficient of static friction. Well, at the fastest speed, before it begins to slip, that means your coefficient of friction, or your force of friction, is at its maximum. So ordinarily, the force of friction is less than or equal to coefficient of static friction times normal force when it's not sliding. But when it gives you the speed right as it begins to slide, then that inequality becomes equal. So the force of friction is going to be equal to coefficient of static friction times normal force. All right, so from our free body diagram, we see that the normal force is equal to the force of gravity. All right, so normal force equals force of gravity. Technically, that's net force in the y direction equals 0. Normal force up minus force of gravity down equals 0. So we take that to the other side. We get normal force equals force of gravity, which is mass times the acceleration due to gravity. All right, so next part is the force of friction. Well, if you look in the horizontal direction, net force in the horizontal direction equals mass times acceleration. The force of friction is the only horizontal force. That equals the mass times the speed squared over the radius. Okay, so the speed squared is given, the radius is given. So what is not given is the mass. We don't know the mass of the coin. All right, but we do know that the force of friction is equal to this equation. The normal force is equal to this equation. So when we plug force of friction into this equation, and then we plug normal force in here, what we get is mass times the speed squared over the radius for the force of friction equals the coefficient of friction times the normal force, which is mass times gravity. And from that, hopefully you notice, is that the mass cancels. So the mass of the coin doesn't matter. So bringing that acceleration due to gravity to the other side, I'm going to write it over here. Coefficient of static friction. Okay, bringing gravity over to the other side, we get speed squared over radius and then divided by gravity. Radius is given, the speed is given. Remember, the speed is given in centimeters per second. You got to convert to meters per second. And then the acceleration due to gravity, obviously 9.8. And actually, they give you the speed in centimeters per second. They give you the radius in centimeters, and they give you the acceleration in centimeters per second squared. Technically, you could leave it all as centimeters as long as that's all the same unit. I know I always say that you got to put it in base units, but that's just for consistency's sake. But really, they all just need to be in the same unit. Technically speaking, they all just need to be in the same unit. But a lot of people have a hard time dealing with that, so I'll just say base units. Makes it easier. All right, other questions? Number 11. Okay. Give me just a second. I hear my daughter's coming upstairs. Let me deal with this for a second. I'll be right back. Hey, can you hit play again? Watch one more, okay? Because mommy's busy and daddy's busy, okay? So one more. Can you do that? Yeah, mommy's in there.
I can't figure out which one.
That's okay. All right, you good? All right, love you. All right, number 11. Okay, so this one so number 12 was rounding the curve, see what was most comfortable. Number 11 is dealing with the force that the road exerts on it. So we're going to assume that it's a flat track as you're going around, and this is going to be that's my car. All right, not a great looking car, but it's my car. It's a dot. So the forces that are acting on it, we got a normal force that is up. That's supposed to be straight upward. We got force of gravity that's downward. And then we got the force of friction. That's what's keeping it on the circle. That's what's keeping it from sliding off. It says, what force must the road exert on the tires to hold the car on course? So basically, we're talking about this force of friction. It's asking, what is that force of friction? Okay, so net force equals mass times acceleration. The horizontal direction, the only forces that are acting are the force of friction. That's going to be equal to mass times centripetal acceleration. It gives you the speed and it gives you the radius. Okay, so we have the speed and we have the radius. So speed squared divided by radius. All right, so essentially that should be it. Mass times the speed squared divided by radius. Let me double check, make sure it is that simple. Speed squared divided by radius. Yep, that's it. So since the force of friction is the only force acting in the horizontal direction, then that's going to be the only force that comes into the net force. All right, number 9. Racing car traveling on a circular race course with a radius and a speed such that it makes that many revolutions in 1 minute, and given the mass, what's the centripetal force? Okay, so centripetal force is the net force. Net force equals mass times acceleration. So I just need to find that mass times the centripetal acceleration, which is speed squared over radius. Okay, now it gives me the number of revolutions per minute, and that gives me period. Revolutions per minute, and technically it's not period. Technically that is that's an angular velocity. Revolutions per minute is an angular velocity. But what I can do is I can take this, and I can take that. Mine says a certain number of revolutions in 1 minute. I could take that 60 seconds divided by the number of revolutions, which I think everybody's going to be different. So number of revolutions. So what that does, when I take 60 seconds and divide it by the number of revolutions, that gives me the number of seconds per revolutions. Seconds per revolution. So whatever that number is on the bottom, everybody's going to be different on that. All right, so that gives me the period. Then I can use that period, take 2 pi times the period, and then divide by the radius, which the radius is given in the problem. Yeah. And then once I do that, 2 pi times the period that's given here, divided by the radius, and I plug it in over here, and I can get my net force, which is my centripetal force. So I'm not looking for a specific force, which is why I didn't really draw a free body diagram, because a free body diagram helps me to define individual forces. But if I can find that net force, that's all I need to do to find centripetal force.